So as we continue our study of friction, static and kinetic, the other thing that we know about frictional force is that it is approximately proportional to the normal force. So sort of the force that's holding the surfaces together, if you will. Now proportional means, when we think about things that are proportional, that means sort of like a doubling. If you double the cause, that corresponds to doubling of the effect. Okay, so in this case, the cause and the effect are how the normal force sort of affects the frictional force. Let's take a look at this single book maybe on a table. Well, if this blue vector represents the weight and the black vector represents the normal force, we know that those are equal amounts. If I start to exert force on this thing and I try to move it maybe to the right or to the left, let me put a little arrow up here to show the applied force. Eventually that's going to sort of break that thing free. If I keep increasing the value of A, eventually that's going to break that thing free. Well, let's just use a different color here and call that Fs max. So at some point I'm going to get to that object moving, and so at that point I would just have exceeded Fs max. Now if I have the same surface that's in contact here, the book on that tabletop, if I simply double the weight of that object, so now I've got twice as much weight, that means I have twice as much normal force. Well, what that would mean is that I would end up having twice as much static frictional force. So this value, Fs max, would end up being larger as well. And that means simply that I would have to exert twice as much applied force to get that to go. And so the idea behind a proportionality is that doubling the normal force sort of doubles the frictional force. Now we can write that as an equation. And so the equation that we're going to write looks something like this. The frictional force that's present depends on the normal force, and this little value mu, it's a Greek letter mu, okay, Greek letter mu, is what's called the coefficient of friction. Okay, the coefficient of friction sort of tells us how much friction we have as a proportion or as a portion of the normal force. So it's like a multiplier. It's different for every pair of surfaces. This table here is showing different coefficients of static friction versus kinetic friction, and those coefficients are different for every pair. Now these are done just experimentally. We don't really know how to determine the coefficients of friction with theory. We just can do this with experiments. So we pull and push on objects, a wood object on a wood surface, and we measure how much force it takes to keep it going, how much force it takes to get it going versus how much force it takes to keep it going. And then we simply compare. If we consider how we might be able to find mu from that, is we might take mu as a ratio of frictional force to normal force. So we would just simply take the amount of frictional force that's acting and divide it by the amount of normal force acting, and there we can get the coefficient of friction. Okay, so mu sub s versus mu sub k. Now if we go into graph this, if I wanted to look at how the frictional force is related to the normal force, let's draw a couple of graphs showing a low friction. I'm going to use green for that. Low friction. I'm going to use wood on wood. So if I consider a wood on a wood surface, I see mu sub s is equal to 0.4. So that's relatively small amounts of friction compared to other things. Okay, so we're going to look at wood on wood. Well, if I were to go to draw how the frictional force relates to the normal force, this is an equation of a line. It's of the form y equals mx. So instead of y, I'm going to use frictional force. Instead of x, I'm going to use normal force. And m really is the slope, sort of represented by that value of mu. So a low friction surface, something like wood on wood, would have a relatively small slope. If I were to exert 10 newtons, if I were to have a 10 Newton normal force acting between the wood on wood surfaces, I would expect that I would need to have 4 newtons of force needed to be able to break it free. So if 10 newtons was sort of pushing them together, I would need 4 newtons to break it free. Now, if I were to double that 10 newtons and make it be more like 20 newtons, so I made it twice as heavy, maybe, and increase the normal force twice as much, then I would expect that I would get 8 newtons of frictional force that's acting. So again, we see the proportionality there. Now, if I had a high friction surface, like let's consider, let's say rubber on dry concrete. Okay, so let's use maybe blue for that one. If I take rubber on dry concrete, I see I have a different value of mu sub s. Mu sub s here is 1.0 as opposed to 0.4. So now when I go to draw the relationship between frictional force and normal force for this, let's do this as high friction, where mu sub s is equal to 1. What I see here is a much steeper slope. Okay, so for a 10 Newton normal force, what I would see is that I would have about 10 newtons of friction. For a 20 Newton normal force, what I would see is that I'd have 20 newtons of friction.